Hello, my name is Elizabeth Gordon, and today I will be presenting on knee torque and the predicted force exerted on those with and without hypermobility. Hypermobility is a condition where a person's joints move beyond the normal range of motion. It is a very common condition, and an estimated 1 in 10 people have some form of hypermobility. Hypermobility can cause a range of symptoms in those affected. Some may never know that they are hypermobile, while others suffer severe pain and dislocating joints. Today, I will evaluate an application of physics on this health issue and investigate how the knee torque of hypermobile people compares to the knee torque of non-hypermobile people in terms of the predicted force applied in the torque equation. In order to calculate the torque, we must first find the equation to use. We will set the torque as equal to the radius times the force times the sine of the angle of the lever arm. In this scenario, we will consider the lever arm to be the lower leg. Then we must set the constants for the equation. We will set the radius at 1.905 centimeters cubed, which is close to the average value of the radius of an adult's kneecap. We will then convert this to the SI unit of 0.01905 meters. The kneecaps are generally fully developed between the ages of 10 to 12 years old. The group used in the study I will evaluate today ranged from 7 to 11 years old. Due to the lack of research on knee joint radius by age, this may result in slight inaccuracies in measuring the torque for children. However, standardizing the knee measurement will still allow for a general comparison between hypermobile versus non-hypermobile groups. In the study, the torque is measured at two angles, 90-degree flexion to 10-degree extension. The types of torque measured in the study are the peak eccentric flexors torque, peak concentric flexors torque, peak eccentric extensors torque, and peak concentric extensors torque. In this evaluation, I will focus on the torque of the peak eccentric flexors. This is because eccentric flexors are very important in everyday activities such as running and walking. Additionally, flexors have shown to be very important in terms of shock absorption and knee stabilization, which can be an issue for those with hypermobility. Since we are evaluating the torque at a point of flexion, we will set the angle at 90 degrees. After this, we will set up two equations, one for the control group and one for the hypermobile study group. We will set the values of the torques as those provided on the table shown here. For the purposes of efficiency, we will ignore the uncertainty values and only use the constant values provided in the table. The value of the torque for the control group is 0.9 Nm over kg, and the value of the torque for the study group is 0.5 Nm over kg. The goal of this equation is to solve for the estimated force applied in order to achieve the torques given to both groups. First, for both, we set the initial equation to torque equals radius times force times sine theta, where theta is the angle of the lever arm. Then we isolate the unknown force variable in both equations, setting the force equal to the torque divided by the radius multiplied by sine theta. In the control group, this equation ends up as force equals 0.9 over 0.01905 times sine 90. This sets the predicted force experienced by the control group as 47.24 newtons. Then we will do the same for the study group with hypermobility. This equation ends up as 0.5 divided by 0.01905 times sine of 90. This equation estimates that the predicted force experienced by the hypermobile study group would be roughly 26.25 newtons. After solving these two equations, we can see that the hypermobile study group has a much smaller predicted force than the control group. In fact, the estimated force of the control group is roughly 1.8 times larger than the study group. This difference demonstrates a major difference in how the knees of hypermobile versus non-hypermobile people might absorb force. A potential explanation for this difference in force could be due to the difference in maximum angle extension. Hypermobile people can manipulate their joints to larger angles than non-hypermobile people. So this may mean that they can achieve larger flexion with less force than would be required to achieve the same angle by non-hypermobile people. With further evaluation, this could also mean that it requires much less force for those with hypermobility to have their joints reach a dangerous level of bending. This could increase the risk of hypermobile people breaking their bones. Hypermobile people are at increased risk for bone fractures, which could be partially explained by this reduced force required to reach different bone angles. And these are my forces.